Oh yeah. So Koshal asks, how will we do the exams? Because we're all going to meet online. Well, the reason we're delaying, one of the big reasons we're delaying the exams, is I have no idea. I mean, I have some faint ideas. There's some proctoring services, um, of various types, but the honest truth is I really don't know. So that's one reason why we're at least one reason why we're going to delay exam two until after break, because well, it might be more like this. And when I say after break, I really mean who knows. Um, I mean, I think I don't know. If I had to guess, I would actually guess that we will probably, instead of having two exams after break, we'll just have one, and sort of in the middle. But we'll sort of see what happens. Like I said, all plans are. I hope I said this before. All plans are written in sand. Especially, that's sort of always true, but it's definitely true now that the world's on fire. But we're going to be okay, right? Is everybody doing okay in their shelter in place? Give me a Y or a yes on the chat. If I hope. Yeah, and I hope everybody's taking a. Oh, hey, Marcel, you made it. San Francisco is fine. It's very quiet. Thanks, man. Um, Marcel, did you want to say a word about how you picked those songs by Mac DeMarco and Stereolab? You just want to say LOL. That's fine. Did you want to turn on your mic and say a bit about that music and sort of
Hello?
yeah, hi.
Oh, hey. Sorry. You probably listening. You're probably also hearing a TV in the back.
Oh, that's
Um,
okay.
no, I just thought they were good music to study too. That's all.
Yeah, so excellent. And I'm hoping Stephen, I will remind you by email to send me some songs, because it turns out Stephen is also a Mac DeMarco fan. Okay,
That's great.
so
That's great.
yeah, so I mean, I'm hoping that let's this is a pretty nutty time, and let's try to make the most of it, and we'll sort of if we're gonna do some stuff online, we might as well take advantage of this YouTube Premium subscription I just paid for, because this is what my family we're sitting around. We are watching a lot of streaming stuff right now. Okay, let's get back to math. Any questions before about what's happening? So I mean, to the extent possible, we're going to try to have a normal week. We'll have a problem session on Friday, except online, and the outline is due tomorrow night for problems at 7, and we'll talk about the problem set itself on Friday, and then see if we can make some progress on it by Wednesday the 25th. Okay, so any questions about what is to be done before we move on? Oh, yeah, I had some revisions also due on the 25th. Don't worry. Yes, so thanks. Yes, uh, let's postpone that until after break, or at least you can try to do it by the 25th. But if you want to work on it over break, that's fine too. I'm going to be, like I said, I'm already, but I'm sure you've noticed, but by nature, I'm already kind of flexible about deadlines, and hopefully, I won't let them go into total disrepair, because they're not unhelpful in forcing people to finish things. But yeah, I mean, there's um, definitely there will be some flexibility in that. Okay, thanks, Dan. All right, let's go ahead. Let's go ahead and pick up where we left off. All right, so last time, the very last thing we talked about is how the Hamming distance. Um, actually, I should. Oh, let's do it. Let's do a little exercise. So, yes, let's see if everybody remembers something about the definition of Hamming distance. So let's make up a random word. And here's another random word. Oops. So, does anybody remember the Hamming distance between those two words? 5. Okay. Ruse, okay, great. So there's a bunch of 5s coming up. And hopefully everybody saw that, let's see, why is it 5? Well, 1, 2, 3, 4, 5. Oh, well, yeah, there we go. So it's actually these 5 coordinates right here are exactly the coordinates that need to be changed to get from the vector x to the vector y. Distance 5. Thank you, those of you who spoke up. So those 5 coordinates are exactly the 5 coordinates that need to be changed to get from x to y, and so the Hamming distance from x to y is exactly 5. Thank you very much. Very good. Yes, because remember, the Hamming distance between two vectors or between 2 words or between 2 bit strings is the number of coordinates or bits or whatever that need to be changed to get from one vector to the other. And the thing that's it's helpful to think of Hamming distance as being defined by paths, a path where you change one coordinate at a time, because that tells you that the Hamming distance satisfies the triangle inequality. So that's sort of that's what makes it a distance. And again, if you didn't quite absorb last time what the triangle inequality is about, or you sort of don't remember, that's okay. What the triangle inequality says, if I can get triangle inequality says that there's no shortcuts. You can't take a shortcut in your travels by adding a destination. There we go. Oh yeah, so Than is asking, how are we going to apply this? The way what we're about to show is that in the next slide, Than asked an excellent question, like what is the point of this stuff? Why are we talking about distance? The reason is that it's through thinking about Hamming distance that we're going to explain this theorem that error correction comes from minimum So the idea here that we're about to get to is that error correction comes from a large minimum distance. A large minimum distance. So we're going to use this idea of the Hamming distance as a distance, as what you call a metric. To explain why it is that a binary linear code with a large minimum distance can correct a lot of errors. So, Than, does that make some sense? Thank you for asking all these great questions. Okay, so yeah, that's how we make money. Yeah, we're going to use this idea of distance to identify the codes that are good, the ones that are going to make us a lot of money. All right, so the somewhat impractical method of error correction that allows us to show that that minimum distance makes error correction possible is what's called nearest neighbor error correction. So the nearest neighbor error correction method in a particular binary linear code is so what you need to do this, it's not practical, but in some sense, this is what you need. What you need is a list of all possible vectors. Here, if you really wanted to do this in practice, I think in practice you actually sort of wouldn't, but receive vectors y and their nearest neighbors. Oops. All possible. Yeah. Received. Right. So in order to actually make the nearest neighbor, so the nearest neighbor error correction method is for every possible vector that you might receive. So remember, y is the vector that you might receive. Again, you want to think you're Yolanda, and and you're getting a transmission from your friend Xavier. And what you want to do is you want to make a list of all possible vectors y that you might receive, which is actually by when I say all possible vectors y that you might receive, you have to make a list of all 2 to the n possible vectors that Xavier could possibly that might possibly come to you. So it's a long list, which makes this method kind of impractical. But the idea is that if there is a unique if for every y prime, I should put that in. Right. So having received a y, if for every y there is a unique y prime that has a smallest possible distance, then that gives us a unique way to correct every possible received vector's y to its unique nearest neighbor. And the idea, and I guess the sort of moral justification for this, justification for nearest neighbor the nearest neighbor idea is that the correction involving the fewest number of changes, that is the correct code word, the possible correct code word that has the shortest Hamming distance to what you actually received, is the most likely intended message. Since fewer errors, since it's more likely to have fewer errors occurring. I mean, unless you have a really horrible, unless you have some sort of super horrible communications channel where somehow you're more likely to get the wrong message than the right one, then it's actually true that if you assume errors are somehow kind of random, then you're more likely to have fewer errors than more errors. And so the most reasonable correction to make is the correction to a possible intended code word that changes the fewest number of coordinates. All right. So anyway, so the idea is the nearest neighbor error correction method will, going along that reasoning, the nearest neighbor error correction method will take a received y and correct it to the y prime that requires the fewest number of erasures. So that's the nearest neighbor error correction method. I think we mentioned that last time, but so now we're going to use this here. So so the idea is, so let C be a binary linear code with a minimum distance d. Then the nearest neighbor method applied to C, which is not necessarily a practical method. It's not the fastest method. It's not the one you would use in practice, but we just want to show it's possible in theory that there is some method, even if it's sort of very slow or very awkward, that is possible to correct at up to say d. The floor of d-1/2 errors. Yeah, what does that mean? So we will discuss this idea, why it is that if your minimum distance is a minimum distance, if you have a code with minimum distance d, that you can correct that many errors. Right. So let's talk about why that's true. So let me make the box bigger here to say that we can correct up to floor of d-1/2 errors. So floor, remember, floor is the floor. If you didn't catch this in the reading, or you're not familiar with this from other things, the floor of an integer is the largest integer that's less than or equal to d-1/2. Is the floor mean? Actually, let me put it this way: floor means round down. So this is what this is saying is that the number of errors you can correct is d-1/2 rounded down. So to say that we can correct up to 4 of d-1/2 errors means that we can correct up to e errors as long using the nearest neighbor algorithm, as long as 2e plus 1 is 2e plus 1 is less than or equal to d. Right. So suppose our minimum distance. Remember, the minimum distance of a code is the fewest number of ones in a non-zero vector is d, and suppose also 2e plus 1 is less than or equal to d. So what happens is if we can't, if there's some way to have to find e possible errors in an intended code word, in a transmitted code word x. So remember, we have our two friends, Xavier and Yolanda, and so the situation where you cannot correct e errors, code word x, that would mean that there are two code words, that there's a possible received message y, and two code words x and x prime, both of which have distance at most e from y. Ooh, I think, hang on a sec. Let me, look, I learned how to do a new thing since we last met. I learned how to do this. Look at that. I can add a new blank page. Everything's different now. Okay, so anyway, so as I was saying, so if there's some e errors that could occur in a transmitted code word that could not be corrected by the nearest neighbor algorithm, that would mean there's something y that Yolanda could receive, and two code words x and x prime, each of which have distance at most e from y. And so here's the picture that we're going to draw. So everything comes down to this picture. So here's, and again, it's very helpful to think of this. And so Than, you're asking, like, why on earth do we need this distance business if in order to make money by correction? And so it's exactly that. This distance business allows us to draw this picture to understand what's going on. So the idea is, if we have two code words that are e errors away from our possible received vector y, then x is a code word. So remember, we have this idea of being in the code and out of the code. So remember, our code C determines what possible vectors that Xavier could possibly transmit. And so whatever Yolanda gets, so Xavier transmitted some x, and then Yolanda gets y, which is some messed up version of x, but it has some errors in a bunch of places. So whatever Yolanda gets, Yolanda has to knows ahead of time what is the list of all possible things that she could possibly receive. And so what happens here is that if there's some ambiguity, then what has to have happened is that there are two code words that are very close to y. So there's this code word x that's within distance e of y, and there's a second code word x prime that's also within distance e of y. So does that picture make some sense? Are there any questions about this picture? So because once you understand this, so there's something like this. So I should say there's something like this on the homework. There's a sort of you're going to do the sort of the error detection version of this, I think, if I remember correctly. And excuse me. And so so the key thing is for you to understand this picture, and that's kind of what's going to allow you to do this homework. So are there any questions about this picture and what's going on here? Okay, everybody's sort of, I think, at least sitting tight to see what happens. Let's try another color. And so the key point of Hamming distance being a distance, it tells us that if the distance from x to y is at most e, and the distance from y to x prime is at most e, then the distance between x and x prime is at most 2e. That's the triangle inequality. The triangle inequality says that we can't make that the distance from x to x prime cannot possibly be any longer than the distance that we get from going from x to x prime through y. And we know that you can get to x from x to x prime through y with at a distance of most in a trip that takes a distance at most 2e, and so the shortest distance is at most 2e. So there it is. This picture here is the key picture to understand. This is the whole point of Hamming distance being a distance. So, and why is that? So if we had some uncorrectable received vector y, then we would have two code words x and x prime, such that the distance between x and x prime is less than or is at most 2e. In that case, the distance between so there by some results that are kind of explained in the chapter, the distance between the vector x minus x prime and 0 would be less than or equal to 2e, which would mean that there is a code word with at distance, there's a non-zero code word x minus x prime at distance less than or equal to 2e from 0. But what were we assuming about the minimum distance? We were assuming that the minimum distance is, wow, I did not mean to do that. Okay, that the minimum distance is at least 2e plus 1. So, but the minimum distance is at least 2e plus 1. So, contradiction. So it must be the case that each received vector y has at most one neighbor within distance e. So nearest neighbor works. Nearest neighbor, the nearest neighbor algorithm corrects up to e errors. Whew. Sorry, I think that was kind of deep. All right, anyway, so Than, I hope that kind of answered your question. That was like, why on earth would you want to look at this distance thing? It's because this distance allows us to think of, at least to think of this result that the minimum, that wasn't what I wanted to do, that the minimum distance, I missed, that minimum distance allows us, having a large minimum distance allows us to correct a larger number of errors, and which is, I know, something I would never have thought of. It would just make no sense to me at all if it weren't for this idea of distance. Okay. All right, so that's kind of heavy. If that didn't make sense the first time, hey, we're recording this on YouTube, so you can watch it again. Especially when you go to tackle the homework. There's another version of this in the book, and so hopefully between watching this once, maybe watching it again on YouTube, and doing the homework and reading the book and doing the homework, it'll start to make some sense. But yeah, if it doesn't make sense the first time, if it doesn't kind of make sense right now, don't be discouraged. This is kind of a deep idea, and well, and so it's useful, and so you can actually make money from it. But for now, are there any questions for now about the idea of Hamming distance and sort of what it tells you about minimum distance before we start something completely different? Okay, so yeah, so try to understand this picture, and then oh, hi, Than, go ahead. Or you can just turn on your mic if you want to ask it out loud. Is this related to the Hamming graph? So I think by the Hamming graph you mean the sort of cubic thing that we were drawing last time? Or like, yeah, this is, yes. So, right, so there's part of it. So the Hamming graph, oh, yeah, oh, you guys did the Hamming graph in graph theory, fantastic. All right, so the Hamming graph is a graph which has which we mentioned last time. Yeah, we mentioned last time, but let me remind you. Is so this is for this is the Hamming graph for f2 to the 3, and there's a similar graph for f2 to the n, and that's the n-dimensional cube. And so let me remind you from last time that yes, this is very closely related to the Hamming graph and graph theory because we can think of so to answer Than's question, the point is that Hamming distance is is a path distance in the Hamming cube. So yeah, in fact, the way that we actually saw that the Hamming distance is in fact a distance that satisfies the triangle inequality is exactly because we think of Hamming distance as being as the length. So the Hamming distance between two vectors is the length of a shortest path in the Hamming cube between those two vectors. Hey, that was better than what I actually wrote. Let me try that again. That's better than the first thing I wrote. So let me try that again. So to answer your question, the Hamming distance between x and y is the length of the shortest path in the Hamming cube between x and y. So yeah, Fan, that's exactly right. Yes, Hamming distance is related to the Hamming graph, and in precisely that way. And it's actually thinking about Hamming distance as being sort of determined by paths within the Hamming cube that actually allows us to explain why Hamming distance satisfies the triangle inequality. So, Fan, does that answer your question? All right, probably even over answered the question. In any case, let's put a button on this discussion, and now let's move on to something completely different. Oh, can we imagine the triangle as? Oh, yeah. Nat has a really interesting question, and I will, which I'm gonna. Um, oh, I can't resist. If we need a little more time to do things, that's fine. World's going nuts. Okay, so Nat asks, can we imagine the triangle and as one face of the cube? Well, not exactly. So let me just type in your question. It's a really interesting question. So Nat asked, let me put this in blue. Can we think of the triangle and the triangle inequality as one face of the cube? And the answer is any picture you can actually draw is not going to be very any realistic picture of a triangle in the Hamming cube won't look much like a triangle. So let me give an example. So all right, let me start with the Hamming 3 cube, but I reserve the right to make this into the Hamming 4 cube if okay. So there's the Hamming 3 cube. Yeah, so this is the Hamming 3 cube that we just drew there, right. And so what I want to do now is I want to try to draw. Okay, so let's see. Okay, so yeah, so there's one side of the triangle, that green path. So this is one vertex. So I'm going to draw a triangle ABC. Triangle ABC. It's going to have three sides, as triangles do. Right. So here's A, and here's B, and I'm somewhat randomly going to make. Oops. I guess I'm going to somewhat randomly make. Put C over here. Here's triangle. Here's vertex C. Okay, so as I was saying, this triangle will have three sides, as triangles do. One side is going to be green. The next side is going to be orange, and the orange side is going to be this to that. And the third side is going to be purple. Yeah. So what happens is that's one example of a so-called triangle in the Hamming cube. Uh, Yeah, it doesn't look much like a triangle, huh? So, yeah. So, but Nat, I think maybe the best answer to your question, sort of, well, at least a decent answer to your question, is that a triangle. If you want to try to imagine the triangle, um, it, in a sort of realistic way inside the Hamming cube, you just sort of probably the best way to do is to take 3 points and then just draw a shortest path from between any two, and that's what a triangle looks like. Um, but in practice, it's probably better to have an abstract picture. So this is one of these things. I mean, one of these odd things that happens when you're dealing with this kind of level of abstraction. It's actually better to It's better to have an abstract picture than a concrete picture. So this is let's see. So orange is AC, and purple is BC, and green and purple was BC. Oops, that wasn't what I intended to do. And purple is BC, and green is AB. So this is what A, C, and B look like. Anyway, I hope if I sort of shuffle between the two pictures, you can kind of see that that in terms of thinking about. I see. Oh, great! I've said so. Than's mind is I've successfully blown at least a couple of people's minds. Um, yeah, but it's better to that's why it's better to think about it as an abstraction. So once you sort of express the distance in terms of an abstraction, you can use this little pretend picture to figure out what the idea is, and then maybe not think so hard about the actual picture in reality. Weird. Okay. I think on that note, oh my goodness, it's let's move on to the next thing. So, any quick questions before we move on to the next thing? All right, and thanks. That was an excellent question. Very strange. It's abstraction is strange, but it's surprisingly useful. Okay, so now we want to talk about yes. So as they say in Monty Python, and now for something completely different. So we're actually going to return to sort of something that looks kind of abstract. Well, I mean, it's going to look kind of abstract because it's quite abstract. It's a pure abstraction, the idea of an ideal. But as we'll see in a bit, it turns out to be very useful. In fact, it allows us to set up the computation for probably the most practical thing that you'll see in this course. So this is going to be quite an abstract idea that will lead to our most profitable thing that you'll learn in this course, which is the finite fields. So on the one hand, I have to say that when we do this abstraction, it will actually be kind of comforting because in many ways it's not as difficult as whatever was going on here. Oh my goodness! Rest assured that once you sort of get a hold of this kind of abstract idea, this is actually what you use at least at some level in the computation of the most practical thing we're going to talk about, which is finite fields. All right, so let's talk about ideals. So again, let's just put on our definitional abstract hats for a bit and talk about rings. So remember, let R be a ring. And so here you want to think, what are the examples you want to think of here? Actually, for us, there are really only two examples I want to think about. You want to think R is equal to the integers, Z, or polynomials, or the ring of polynomials over a field F. And in fact, probably the most when I keep talking about finite fields, the most important example for us is going to be when actually, let me even sort of be more explicit. Oops, that was not what I wanted to do. There we go. So the ring of polynomials f of x, the most important case is where f is equal to fp. The integer is mod p. So I want you to think about, so when I say ring, I really mean for us pretty much the integers or polynomials with coefficients in a finite field. But it's actually takes less time to state the general definition. So I'll just use the general definition. So let R be a ring, commutative ring with identity. An ideal of R is a subset I of R that satisfies the following three axioms. Ooh, I should have numbered these 0, 1, and 2. It's always 0, 1, and 2. Oops. So the axioms 0, 1, and 2 are as follows. Axiom 0. So an ideal has to contain 0 elements. It has to contain the number 0. Axiom 1 is that an ideal must be closed under addition. And axiom 2, an ideal must be closed under multiplication by elements of the ring. So 0, closed under addition, and closed under R multiplication. All right, so that's what an ideal is. So that's total. So the first thing, okay, so let's do some training in abstraction. So when you see an abstract definition like this, that's this definition of ideal, it seems to come out of nowhere, and you have no idea what this is about. The first thing you should do when you see this is you should say, I want to construct some examples myself. So, and if you're really well trained in abstraction, the first thing you should do is close the book, so to speak, or sort of put away whatever it is that you're reading, and try to make an example for yourselves. Now, I mean, I'm going to do an example for you, but ideally, if you guys could be trained to the point where when you see a definition like this, you'd say, I want to make my own example. Ah, fantastic! That'd be wonderful. Anyway, okay, we're not going to be too crazy about this. So let me actually sort of look at an example. So the sort of canonical example for this is sort of the standard example. One of the standard examples of this is the multiples of 3. So let I be the set of all integers that are 3 times some other integer. So oh, actually, can you guys type in chat? So can you name one element of I? So what's some integer n that is 3 times some other integer? So just type this in chat. 6. 6039. So 0, 3, 6, and 9. Any others? Or -3. That's So good. So there's -3 is also 3 times an integer, and okay. So that I think that's enough to give the idea. So if I is that set, then this is these are the elements of I. It's going forward 0, 3, 6, 9, 12, and 15. Thank you. 12, 15. And going backwards, you get 0, -3, -6, and going down to -infinity. All right, so that is our set. And I want to. So now what I want to do is I want to prove / explain why. Explain why / explain why I is an ideal of Z of the integers. Oops. An ideal of the integers. Okay, so first of all, to do that, I need to prove that, or explain why 0 is in I. I need to prove or explain why I is closed under addition, and I need to prove or explain why R is closed under taking multiples, taking integer multiples. So let me go ahead and do that. So why is it that 0 is in I? 0 is equal to 3 times 0. So 0 is an element of I, right? Because 0 satisfies the defining relation. So remember this bracket slash bracket stuff. 0 satisfies the defining relation of I, and so 0 is an element of I. So questions so far? Okay, so so let's talk now. Let's turn to explaining why I is closed under addition. So remember to show that something is closed under addition, we assume we have two elements of I, and eventually, so that's our assumption, and so our corresponding conclusion is we want to show that x plus y is in I. So everybody, any questions about you remember that kind of? Well, I mean, actually, so see if we get a yes, some yeses on the chat window here. Do you all remember that this is how you show that a set is closed under addition? Yes, Than wisely points out that yes, this is exactly like something you saw in linear algebra. Yes, this is very much like proving a subspace, proving something's a subspace. Okay, so because x, we're assuming that x and y are in I, so x is equal to 3k, and y is equal to 3, let's say m, for some integers k and m. Some k and m in the integers, and remember they're not both k. You can't use you don't want to use the variable k for both of these, the right hand sides of these equations, because uh, x is going to be 3 times as 3 times some integer. That doesn't mean y is going to be 3 times the same integer. It's going to be 3 times some other integer. And so and we're going to want to arrive at the same kind of conclusion over here. We're going to want, and the end result of this is going to be, so x plus y is going to be 3 times some x plus y is going to be equal to 3 times some integer. Therefore, we will reach the conclusion that x plus y is in I. So does that make sense? Like, this is where we're starting. You know, as I always say, proof is like driving from San Jose to Los Angeles, and you always want to think about where you're starting and where you're going to end up. So everybody good with that so far? Okay, get some yeses. All right. So so what that means is that so therefore x plus y is equal to 3k plus 3m, which is equal to 3 times k plus m. And so we're done. And so x plus y is equal to 3 times some integer. It's k plus m is some integer, doesn't matter what it is. And therefore, k plus y, x plus y is an element of I. I is closed under addition. So good so far? Okay, we have a few yeses here. All right, let's do close under our multiplication. Well, again, we're going to assume that x is in I. Somebody want to type in the chat what that means? So thank you, Alexis. So x equals 3k for some integer k. And so the end result, oh, right. So we're going to assume, sorry, I left out an assumption. And we're going to also assume that we have some other element in z. So there's just some other integer in z. But not necessarily something in I. So we're not. So this is a subtle point. So so the subtle point here is we're not just showing that I is closed under multiplication by elements of I. So we're not just showing that I is closed under multiplication by elements of I. Uh, we have to allow multiples from coming from outside I. So this is the most subtle aspect of the definition of ideal. So ideals are not just closed under multiplication within themselves; they're closed under multiplication by stuff outside the ideal. All right. So in any case, so I'll let you mull that subtlety for a while. In any case, the conclusion that we want to reach is that n times x is in I. So, in order to reach that conclusion, what we're going to do, how are we going to get n times x to be an element of I? Well, we need n times x to satisfy the defining condition for being in I, and so we'll need that n times x is going to be equal to 3 times some integer. Therefore, conclusion, nx will be an I. So, is everybody good with the outline so far for showing that that I is closed under R multiples? Yeah, this might take a little doing here. So let me. This might take a little. This takes some getting used to. So let me just point out that the sort of outline. So I think one of the things that you have to do, I think this is on problem set 7, but if not, it'll be on problem set 8. One of the things that you have to do in order to complete your outline for a problem where you have to show that such and such is an ideal is that you have to be able to you have to sort of understand. I can't write sideways. I tried, man. So one thing you want to do if you go back when you go back and do some more of your reading, do the reading again, or if you study this lecture on YouTube, this is a point that you might want to sort of look at and rewind. Is that look at the outline of showing that a set is closed under addition, and especially is closed under multiplication by the outside ring, multiplication by elements of Z and not just elements of I. Okay, so that being said, once you sort of figure that out, once you sort of figure out the outline, it's not too bad. Once we have this assumption that x is equal to 3k for some k and z, we can see that n times x is equal to n times 3k which is equal to 3 times kn. Oh, yeah, and that's it. Then we're done. So nx is equal to 3 times some integer, which means that nx is an element of I. And now, look, we did our first proof for oops, that's not what I wanted to do. We did our first proof for ideals. Now we've shown that 3 times the now we've shown that 3 times Alexis, excellent question. Let me get to that in a second. Now we've shown that the multiples of 3 are an ideal of R. And so Alexis asked the question, we're proving that I is an ideal of Z, right? Because it wouldn't be an ideal in other rings. That's exactly correct. And I think it's probably most instructive to point out exactly where the sort of underlying ring occurs. So it's exactly here. So we're showing, as Alexis was asking, we're showing that this is an ideal of Z, and not necessarily of some other ring, like the real numbers or the complex numbers or whatever. And the way that actually enters into what we're doing is exactly here, where we have to show that I is closed under multiples in Z, because, for example, I, as Alexis is asking about and perhaps pointing out, so I is not closed under multiplication by, if you allow all real numbers, if you were to allow all real numbers at this stage over here, if you were to look at all possible real multiples of elements of I, then I would not be closed, because you can multiply by you can multiply 3 by 1/3 and you get 1, which is not an element of I. So yes, that's a subtle question, but that's correct. So yeah, so it's very important that we're proving that the multiples of 3 are an ideal of Z and not of something else. So Alexis, did I answer your question? Okay, great. All right, so any other questions about our very first proof of something, that something's an ideal? Very exciting. Any other questions? Okay. Here's another example. Well, so here, I want to look at the multiples of a fixed. So I'm going to fix some polynomial f of x, and in f bracket x, and I want to show that the set of all multiples of that single polynomial f of x are also an terrible. This is wrong. Yeah, this is what I get for doing this late at night. Okay, so sorry. So let A be all the multiples A of x times f of x in f bracket x. Okay, so first of all, so let f be some field that we unspecified field that is fixed, but if unspecified, and let little f of x be a fixed polynomial with coefficients in big F, and let I be the set of all multiples A of x times f of x in capital F bracket x. So this is well, let me put it this way: let I be the set of all. Oops. I want to type. I might continue to do this in blue. This is all polynomial multiples of little f of x. So you start off with some fixed polynomial little f of x, and you look at all products of that polynomial with some other polynomial in capital F of x. And now I want to show and I want to show that I is an ideal of f bracket x. Okay, so how do we do that? So let me having gone through that process somewhat in detail. Let me actually sort of do it, especially because we're running a little short on time. Let me actually sort of, instead of doing the assumption conclusion, let me just sort of present the proof. So we need to show that 0 is in I. Well, actually, let's see if I do this by typing. Well, the zero polynomial is equal to 0 times f of x. So 0 is in I, because remember I is the set of all whenever I take whenever I get a polynomial that's some other polynomial times f of x, then that product must be an I. So so 0 is an element of I. So good, we checked off axiom 0. So closure addition. So suppose g of x and h of x are in I. What does that tell us? What does that tell us? Then by definition, g of x equals a of x times f of x, and h of x is equal to b of x times f of x. Where a and b are polynomials. Okay, so then what happens? Well, then if we look at g of x plus h of x, then we get a of x times a of x f of x plus b of x f of x, which is equal to a of x plus b of x times f of x. Therefore, g plus h is a polynomial times f of x. So conclusion, g of x plus h of x is in I. So let me go back and compare what we did over here for closure under addition. If you go back and look at what we did over here and compare what we did over here, it's pretty much the same argument. I mean, we have to allow for polynomial multiples instead of just integer multiples, but it's actually really almost exactly the same argument. And closure under R multiples is very similar. So suppose g of x is in I, and suppose we have some I don't know, c of x is in f bracket x. So g of x is in I, and c of x is some other random polynomial. And so that's analogous to over here. We pick some random number that we're going to take as a multiple. That's because we were showing there that I is an ideal of the integers. Over here, we pick some random polynomial, precisely because we're showing that I is an ideal of f bracket x. So yeah, when you do this, you have to sort of pick. When you look at multiples, you allow for multiples basically coming from some random other element of the sort of larger ring in question. So then, by definition of I, g of x is equal to a of x times f of x for some a of x in f bracket x. For some polynomial a. Therefore, c of x times g of x is equal to c of x times a of x times f of x, which is equal to the product c of x, a of x times f of x. So c of x, g of x is a polynomial times f of x. Therefore, conclusion, c of x, g of x is in I. And so we're done. All right, I know that was a little fast, but go rewind the tape, and you'll see that this is really exactly the same argument as we had for multiples of 3. So in general, if you have actually both of those two proofs are special cases of a general proof, which is that if you have a ring R and a fixed little a in R, the set of all multiples, this is the set of all R multiples of A. So that is an ideal, and it's called a principal ideal generated by A. in a very similar in a very similar way, if you have a ring R and two fixed elements, little a and little b and R, this set parens a comma b equals which is a set of all R linear combinations of A and B. And you may recognize this. This looks an awful lot like span. What do I want to do? Let's try this. It looks very similar to the span of A and B. So that set is called the ideal generated by A and B, and there on the homework, it'll be sort of your homework to prove that the ideal generated by A and B is in fact an ideal of R. Okay, so that will happen. And there's there's one other example here, the substitution kernel, and I think I will skip that because I want to start the next bit. But yeah, so there's more. There are more other examples of ideals that to be to look at in the text. Okay, so that having been said, yeah, okay. So I think I can just do this. I think we can just we'll take a few minutes and we'll talk about this definition, and then maybe next time I'll talk about a concrete example. So remember how on day one. Oops, it didn't work. On day, well, not day one. Early on, we didn't quite define Z mod M. So now we can actually finally define it. So, but what we're actually going to do is we're actually going to, because remember this thing, the multiples of 3, right? So, in retrospect, in terms of the notation we develop later, this is also known as, this is also known as, if I can get this to type, also known as parens 3. It's a principal, so this ideal, which is all the multiples of 3, is also known as, if you look at the principal ideal notation that we developed over here, the other name for that is parens 3. And so the reason that we called Z mod 3 Z mod parens 3 is because that's actually a special case of this more general abstract definition. Given an ideal I of a ring R, our next goal is to define the quotient ring R mod I. Okay, so let R be a ring and let I be an ideal of R. So for little r and big R, we define the additive coset R plus I to be the set of all things in the form R plus I. Well, all things in the form little r plus little a are, oh my goodness, terrible. Where little a is an I. Oh yeah, sorry, no, that's not terrible because we already fixed what little r is. My bad. I was about to do something terrible because I'm running out of time, but I caught myself. Okay, so for little r and big R, we define the additive coset little r plus I to be the set of all things in the form little r plus a, where a is an I. So if the context is clear, instead of saying additive coset, we'll just say coset. Okay, so remember, I think this is a good place to stop. We'll just start one example and then we'll pick up here next time. So remember, parens 3, we already said we said that parens 3 which is a set of all multiples of 3, which kind of looks like there's there's -9, -6, -3, 0, 3, 6, 9, and so on. So that's what parens 3 looks like. So can someone just name a random integer? Just type in an integer really quick. 5. Okay, fantastic. So if we look at the additive coset 5 plus parens 3, what you get for the additive coset 5 plus parens 3 is you take all those elements up here of parens 3 and you add 5 to each one. So minus 9 plus 5 is minus 4. Minus 6 plus 5 is minus 1. Minus 3 plus 5 is 2. 5, 8, 11, 14, and so on. So what you get here is instead of getting the multiples of 3, you get the multiples of 3 offset by 5. And all right, so on Monday, we'll look at, oops. So we'll start off on Monday by looking at more examples of R plus I. For I equal, I taken to be the ideal 3 in the integers. Okay, thank you very much for your patience.
Professor?
Oh, go ahead, yeah.
Yeah, I have a question from chapter 6, like it's from the recent homework.
Sure.
There was a question about finding out all the code words for Hamming code H7. Like by code words, do you mean like the bits?
Yeah, so question, what do I mean? So everybody's free to go. You're always free to go, but stick around if you want to hear the answer to this question. So who's asking this?
It's Janvi.
Hi, Genevieve. Okay, I thought I recognized it. So what is meant by finding all, by write down all code words in H7? So that's what you're asking?
Yeah.
Okay, so answer. H7 is a subspace of F2 to the 7. Specifically, it's the null space of one particular matrix. So does that make sense? What would be?
So is it like writing out the basis?
Yeah. So it's not just writing on the basis. So we know how to find a basis for that subspace. That was the whole thing in chapter 5. That problem asks you to write out every vector in the subspace. So it maybe sounds a little bit tedious, right? So remember, the relationship between a basis for a subspace and the set of all vectors in that subspace is, so the set of all vectors in a subspace is the set of all linear combinations of your basis elements. So this is something, all right, and so this is actually like a completely new kind of problem as compared to, I mean, so a lot of the problems that we saw in chapter 5 were very similar kinds of problems from what you may have seen in linear algebra from before. This is a completely new kind of a problem because I couldn't ask you this in, you couldn't be asked this in linear algebra over the reals, because if I asked you to write down all linear combinations of some basis, well, that's infinitely many vectors and you would never finish. But since the coefficients that you're allowed to use, there's only a finite number of coefficients you're allowed to use, you can actually write down all possible vectors. And so yes, it's a little bit tedious, but it's a good kind of tedious. I actually want you to write out not just a basis for that subspace, but actually all the individual vectors. So, John, does that make some sense?
Yeah, this makes sense. Thank you.
And can you remind us what problem this is?
Yeah, just a minute.
It's 6.3 point something. Maybe I know what it is. Hey, if I only had the book right here, right? It's gotta be 6.32.
Yeah, 6.3.2.
Okay. Anyway, I gotta go eat lunch with my family. I should let everybody go 4 minutes ago. I did sort of let everybody go for 4 minutes ago. So everybody who left, you can go see this catch the end on YouTube. Thank you very much for your time. Talk to you later, and stay safe. Stay shelter in place. Go learn how to cook. Talk to you later. Bye.